So thank you everyone, especially Fresh family and friends for joining us on Fresh Big Day today, which is his PhD defense on his thesis topic, interactive scalable interfaces for machine learning interpretability. Yes. So a little bit of logistics. So for today, Fresh presentation will be about 45 minutes long. And I request that everyone hold their questions until the very end. If you have questions during the talk, you're more than welcome to type in the chat window, but do not unmute because then you will overlap with Brett's voice. So you can type your question in the chat window, and then after his talk, then he will address them. And after his talk, we'll follow the standard procedure, which is that Fred will take the question from the audience, and then we'll thank all the audience, and then also kick all the audience out so that only the thesis committee will remain, and then the committee will question Fred. Well, it sounds very scary, but yes, we're asked for a question. And today we're really happy to have our committee joining and other defense. So I'm Polo. I'm a first advisor at Tech, and also we have a first co-advisor, Alex, also at Tech in the School of Interactive Computing. Then we're a committee member, Chau, Zhang, a professor in the School of Computational Science and Engineering. We're at Nathan Hodas, and Pacific Northwest National Lab, Scott Davidoff from NASA, Jet Propulsion Lab, and Stephen Drucker from Microsoft Research. Right, so that would be an introduction for me, and I think we'll let Fred take the time away and start his presentation.
Cool. All right. Thanks so much, Polo. Well, you already sort of jumped to the chase here. I just wanted to thank my thesis committee for the help and guidance that they've given me over the past years. Also want to thank everyone who's tuning in live from my living room, which I'm sure we're all sort of shocked that it's here and not in person, but if there's any upside, it's that there's a lot more people that get to join in today than otherwise would. So really excited to have everyone here. I know we also have some people who may have to duck out early. So I just want to thank everyone just for at least tuning in to see how everything goes. So with that, I think we are ready to get started. So if you've seen one of my talks over the past year or so, you know I like to get everyone kind of in the mood by playing a little game. This little game to see how much or how many different machine learning models you interact with on, say, just one given day. So in this experiment I ran a couple months ago, but still holds true today, which is if you just log all these different technologies, you'll see that before you wake up, your phone can be learning your sleep habits to preserve its battery health. We have autocorrect and different messaging services to help us text better. Well, sometimes we're able to use our face and fingerprint to unlock our phones and access content. Google Maps and navigation will tell us how to get places at what times. Multiple models that are in email clients to help us smart compose, and so on and so forth. Health informatics, social media recommendations. Machine learning is really touching every single part of our lives these days. But as if you've interacted with any of these technologies, you've likely experienced an error. For example, if that phone battery charging model doesn't work, you could wake up and your phone's not charged, and that can be pretty annoying. I'm sure we've all sent the wrong message on a text prediction mishap as well. But more seriously, search results have been shown to spread misinformation. Social media news feeds can actually pigeonhole one's beliefs. And then more seriously, health informatics can actually lead to life-threatening situations. And so the punchline here is that machine learning just makes mistakes. This is a fundamental difference when designing with data-driven models as opposed to more traditional computer science approaches. And then once again, if you've seen any one of my talks for the past 2 years now, you know that I love this slide where if you go to just Google and you want to look at the autocomplete for what AI is, you see there's this dichotomy. It's both dangerous, taking over, but simultaneously it's the future and it's good, but it really is just everywhere. So there's this duality between machine learning being this force for good and helping us, but also making these bad mistakes that's causing people harm. So how do we go about fixing that? Take a look at just the high level view of machine learning. There's two main components. So we're going to take data sets that are collected and curated, and then from those data sets, we train models. But unfortunately, oftentimes those models, what those models have learned is unknown to both the people who train them and then the people they impact. So one thing that's been really prominent over the past few years is this notion of interpretability. And interpretability asks questions such as, what has my model learned? Can I explain its predictions or just understand its behavior in general? But besides just fixing errors in models, there's a whole bunch of other reasons why we may want interpretability. I've listed a few of them here. From legal requirements from the GDPR to ensuring that models are fair across multiple diverse groups of people. Folks are using machine learning at places like NASA for science and discovery. We want to make sure they're robust against attacks, but then also we just want to know if AI is right for the right reasons. This is sort of this fundamental drive, this curiosity. And throughout my PhD over the past 5 years or so, I've had the wonderful opportunity to spend time at a number of different organizations alongside artists, designers, developers, and researchers, all applying machine learning to some of the world's hardest problems. And my assertion and sort of trend I've noticed across all these places is that machine learning truly is a people problem. Let me explain a little bit more about what I mean by that. If we look at the machine learning process a bit more in depth, before we even touch code, we engage with something called task formulation. This is deciding whether or not machine learning is appropriate to apply to one's problem, and if it's even feasible. And this is a process framed and done by people. When it comes to data collection, cleaning, and labeling, these are all processes done by people, and oftentimes this data is describing people. And then when it comes to the modeling, it's people that are the ones deciding what should come in and what should come out of machine learning models, and also setting the metrics by which we evaluate to determine if they can be deployed or not. And so with some suggestive highlighting here, you can see that the common theme is that people are really at the core of every single one of these stages. And then my claim is now that interpretability should really be no different. So in my work, I take a human-centered approach to understand what people really need to design and develop the right tools for interpretability. And this has led me to this research mission that I've been working at my time over Georgia Tech. It's very simple, just this one line, and that's to enable machine learning interpretability at scale and for everyone. And there's 3 important pieces of this mission statement here, namely to enable, scale, and then make sure that everyone can understand machine learning because we know it's impacting all of us these days. And these 3 parts form the basis of my thesis and what I'm going to be talking to you a little bit more today. They also lead to a couple of really interesting research challenges. For example, how do we actually enable interpretability? How can we empower people to interactively explain machine learning models? Secondly, once we have this interpretability capabilities to explain models, how do we then scale that up to bigger data sets, more complex models, for example, deep learning and neural networks that have really been driving a lot of the progress the past few years? And then lastly, as we've seen, machine learning is really touching everyone in so many different ways across different devices that we're using every day. So how do we communicate interpretability to make sure that everyone can get a sense on its impact, its limitations, and the capabilities that it can do? So working towards this mission, I've been working in a number of different research areas, but primarily human-computer interaction and data visualization, and then marrying that with machine learning and some graph analytics as well. So it's a very highly interdisciplinary work that I've been doing over the past years. But today we're of course not going to be talking about all these projects. We're just going to highlight a subset of them that are going to form the basis of my work, and then also speak to those research challenges that I just outlined before. And that's going to lead us to this overview slide. So we're going to come back to this. It's going to be the primary examples I'm going to explain and get into a little more detail today. And at the very bottom, I forgot to mention this at the very beginning, there's this URL. So if you go to fredhohman.com/defense, I realize that the remote meeting isn't ideal for video demos, of which there will be a handful in this talk. So if you want the animations and video demos and perhaps a bit more higher frame rate, you can get PDF printouts and then also YouTube videos there as well that you can view if for some reason your internet isn't cooperating. But now that we've sort of motivated why interpretability is important, let's take a look at some of the work I've been doing to achieve this mission statement that I set out at the beginning. Let's start with enabling interpretability. Let's first just ask this basic question. What really is interpretability? We've already talked about it a little bit today, but we haven't really given it a definition. So if you go in literature and you see what everyone is actually claiming a definition of interpretability to be, you see everyone agrees that it's some human understanding of a part of a system. But then from there, it's actually not quite clear what part of the system should actually be understood, whether that's the internals, the operations, or even just the predictions it makes. And so the punchline here is that there is no formal or agreed upon definition for what it means to be interpretable. And this motivation, this fact really led us and gave us motivation to work on this first piece of work that I want to present to you today with some colleagues at Microsoft Research. And here what we want to do is say, even if there isn't no one definition of interpretability, people are still building models, so we shouldn't let that stop us from helping them understand what the models are learning. So in this first piece of work, it's called Gamut. The title is Understanding How Data Scientists Understand Machine Learning Models. This was published at Chai 2019, one of the top venues in human-computer interaction. And there's three primary contributions with Gamut here. This first one is, instead of offering up yet another definition of interpretability, we instead operationalize what it means for something to be interpretable, and then from that instantiate what we call a design probe that embodies this operationalization. So here we then want to evaluate and see how users and actual practitioners go about using our tool, and more specifically our operationalization, to understand different types of machine learning models. So let's step through each one of these points. How are we going to operationalize interpretability? Well, with some formative research with a number of different professional data scientists at Microsoft, we gave them a prompt that said, in some perfect world, given some machine learning model you maybe have trained this morning or last night, whatever it may be, what are the types of questions you want to ask it to help interpret both the model and its predictions? So we gathered all these questions that people were telling us about and categorized them and sorted them into the topmost ones that everyone was repeating. And we came up with these 6 questions that everyone was asking over and over again. And from these questions, we actually casted them into what we call explainable ML interface capabilities. These include things like local instance explanations, comparing explanations, counterfactuals, and so on and so forth. And in the paper, if you want to go and check out a little bit more in depth, we provide definitions for each of these capabilities, as well as examples to help get you more familiar with what the technique may look like. Okay, so we have this operationalization. How are we going to go about testing it? We're going to use something called a design probe, because right now building models is a common practice, but interpreting them still is not. We're using this method that is really just building some sort of system, getting it in front of people with the hope of just returning with some sort of useful information about some unknown practice. And that meshes really well with what interpretability and how it's situated in industry right now. So let's take a little more in-depth look at what this design probe is actually going to do. Say we have some housing data set with a bunch of different homes, and we have a model that predicts that this house, 550, has a predicted price of about $190,000. Now this house has a number of different features that our model is using to come up with this number. But in our tool, you can actually go about and look at an explanation for how this number was actually computed. So on the x-axis of this chart, we have all those features of the home. And on the y-axis, we have the units of the prediction. So in this case, it's dollars. And you start at the medium home of your data set, and then you either add or subtract a certain amount that each feature is contributing towards your final prediction. So these dark gray bars are actually features that are pulling your house's cost down, and the light gray bars are adding to the final predicted cost. So now we can get a pretty clear view of how this house was given this particular number or this prediction. But in our tool, you can also compare different explanations as well. So we have this other home, this home 798, that has a pretty similar predicted price, but it actually attains that price for a number of different reasons compared to the first home. If you didn't have these visualizations, you would have no idea how these numbers are computed, and you wouldn't know that they actually attain them in a number of different ways. For example, these 3 features that I've highlighted in orange. Now in our tool, you can go up to any one of these different features and hover over it, and it'll tell you exactly what that feature is and how much it's contributing. So for example, this overall qual feature, this describes the material finish and quality of a home. So if you have granite countertops and nice wooden floors, then you're gonna have a high overall qual value. So this house on the top has an overall qual of 8, and that's adding about $22,000 to this prediction. But the overall qual value of the bottom house is 6, and that's actually removing some amount from the average home's predicted price. But say we wanted to look at this feature overall qual over the entire data set, not just these 2 local explanations. We can actually bring this out and get a bit more higher level or a global explanation for this entire feature's impact on our data set. So on this line chart on the left, the x-axis is now the values that this feature overall qual can attain. So it ranges from about 2 to 10, with most of our homes having a value of 5 to 7. And then the y-axis is still the units of the prediction. So in this case, predicted price, or dollars. And here we can now see that you need about an overall qual of 7 or greater to actually add more money to your prediction, which is why there's that difference between the 2 homes that we looked at earlier. And if you're wondering how we're doing this, we're using something called generalized additive models. And the reason we chose this model class is because they satisfy a number of different criteria that we wanted to have during this user study I'm going to present in just a couple of slides. And just for a quick note on the math here, it's very similar to a generalized linear model, but if you replace those linear slope coefficients with these nonlinear smooth shape functions, is what they're called, these yellow f sub n's, you get a bit more of an expressive model class, but you still retain this additive property between the features. So we have this nice high-level explanation for one feature, but in our tool, you can do this for every single feature. So here's a little video demo, just a quick walkthrough of what our tool does. This is Gamut. On the left-hand side, we have all the different features and the shape function charts that we've been looking at, and they're all sorted by different feature importances that could be user-defined. You can add and remove them. You can hide and show various components of the visualizations. And then on the right-hand side, we now have these local explanations that actually describe just a couple of data points, those ones that we were looking at earlier. And all these are interlinked. So whenever you hover over one piece on the right-hand side, you'll highlight that feature on the left-hand side. And by hovering over any one of these line charts as well, you can actually ask these interactive counterfactual questions to see how your home's price would change if you were to maybe expand your living room or add a pool or something like that. And then lastly, because the data scientists that we built this with always wanted to escape to the raw data, we have this interactive table in the bottom that lets people select which data points they want to consider and also compute nearest neighbors in a bunch of different feature spaces or predicted space if you're interested as well. And there's a lot more that Gamut can do, but I just wanted to give you a brief taste of what this tool and system actually looks like before we jump into the study here. So with 12 data scientists over about 1.5 hours each, which each of the practitioners here, we ran a think aloud study, and we were asking these professional data scientists at Microsoft to answer a bunch of different questions about machine learning models, both regression models and classification models loaded into our tool. And we were interested in these three main high-level topics, mainly why they need interpretability and how they use it in our tool versus global and local explanations, and how does interactivity play a role in their explanation process. So just for some quick findings, besides the reasons I had highlighted earlier, unsurprisingly, these practitioners want interpretability to debug and improve their models, but also just to understand large data sets and then engage with some sort of trust building process and communicate that their findings to various stakeholders invested in a machine learning project. When it came to global versus local explanations, people who were more novice users with only a few years of experience within machine learning gravitated towards using these local explanations more so on the right-hand side versus more expert users that were focused more on these higher level, more global explanations on the left. And then perhaps unsurprisingly, interactivity and all the different things that we built into our tool was the primary mechanism that people used to explain predictions and answer the questions. And this is despite that the state of the art before our system was these printouts in the bottom right-hand corner of hundreds and hundreds of line charts for models trained on big data here. And so the takeaways of this study is that we found that interpretability is really not some singular rigid concept, but our operationalization helps people still try to understand and make progress against knowing what their models have learned. We also think that you're going to need to tailor explanations for specific audiences, balancing this notion of simplicity versus completeness. And then we think it's going to be key to effectively design and integrate interaction into these systems to really realize interpretability in the future. But during and after our study, we also noticed that our participants were really speaking aloud and writing down a bunch of notes to really keep in their working memory about what a particular visualization was actually showing them. And we thought maybe systems could actually help people out actually interpreting what a chart is saying by some sort of direct annotation. And so in just one slide here, I just wanted to mention this other extension from Gamut that we call Telegam that goes about combining visualization and then verbalization or just natural language for a better user experience when it comes to interpretability systems. So the main contribution here is that we see those similar waterfall charts that we've been looking at already. But if you're not quite sure what the chart is telling you, or you want sort of the biggest features that you're really interested in, we have this system where you can actually generate natural language explanations for what the chart is telling you. So we have these sentences that'll say, there's two features that are having, accounting for about 33% of your total predicted price, and those are the features you should be really interested in. But the really cool part is that when you hover over any one of these natural language sentences, it'll highlight directly on the visualization which piece or which marks are actually the pieces that it's trying to call your attention to. So now you have this immediate explanation you can just read in natural language. You can then go to the chart and see which pieces that sentence is describing, and then take in the entire visualization for a bit more context. So some of the impact that these two systems have had, Gamut has been deployed at Microsoft Research and has been demoed for their executive leadership on multiple internal conferences. There's a URL here if you want to go and test out some of the features yourself. But it's also been included into InterpretML, which is a really popular open source GitHub project for interpretability. And there's a version that works with Sandance too, which is a really popular visualization tool that's also open sourced on GitHub. But perhaps my favorite thing that came out of this project is when I was presenting Telegram at IEEE Viz last year. And at the end, during the public Q&A, Ben Schneiderman came up to the microphone and asked this question, more so of a compliment, basically saying, what can't this system do? But there's actually a bit more to what he's saying here besides just, wanting to say, how great these tools are. He's really asking, what is left in the interpretability research area that these systems or this operationalization can't cover. And one limitation of Gamut is that we're using that particular model class that only generally works on tabular and numeric data. But we know that deep learning is really making this immense progress on other types of data, such as images and natural language. So how are we going to take this operationalization and scale it up to these larger, bigger models? And that's going to lead us right into the second part of this talk today, which is scaling these ideas and operationalization to larger, more complex models, such as deep learning and neural networks. So as we get started there, we thought it might be a good idea to just see how many different visualization systems have been developed to help people explain deep learning models. As you can see, this is a pretty rich research space over the past few years that's really been exploding with a bunch of different tools. So our first goal is really just to organize and summarize all this work to get a better sense of where are the missing holes and where's the biggest opportunity. So this led us to do this interrogative survey that we published at TVCG in 2018. This is the top and premier data visualization journal. And so the survey is conducted in this interrogative way. So what I mean by that, we're using the question words, such as the ones listed here, to really go through and dissect all the different systems that have been published so far to help people use visualization for deep learning. And the result is this gigantic table on the right-hand side where we fill in all these little dots for every system that correspond to one of the categories, the sort of staple of survey papers. But there's just one important takeaway I want you to get from this table, which is in the how column. So how people are actually going about visualizing deep learning. Well, it turns out that an overwhelming majority, 33 out of 38 systems that we surveyed, are using something called an instance-based analysis technique. So what do I mean by instance-based? Well, we're only looking at explanations for, say, one data point or maybe one neuron in a layer. So let me show you an example of what that looks like. So here we have some sort of neural network model, and it's some image classifier. So we have this picture of a bike. We put it into this model, and it'll tell us correctly on the output that, yes, indeed, this is a bike. But say we have this other bike, slightly non-traditional, and then it gives us the prediction that it's actually a truck. We know this isn't the case, so we want to understand why our model got this prediction wrong. So we use one of these instance-based analysis techniques, such as attention or sensitivity, to understand what parts of the image the model is looking for to make its prediction. But like I just mentioned, these techniques are only focusing on just one instance, one explanation, or maybe just one neuron, for example. But we know that modern neural networks actually compute predictions from millions of weights optimized over millions and millions of images, and these explanations can easily miss a bigger picture. So in this next piece of work that I want to describe to you, our goal is to really scale deep learning interpretability. And the way we're going to do that is by visualizing what we call activation and attribution summarizations. So this work is called Summit, and we published it at VAST last year, the top conference for data visualization. So the main idea of Summit is that we want to scalably summarize and interactively visualize neural network feature representations for millions of images. Now, how are we going to do that? Let's take a collection of data examples or images, say an entire class like the white wolf. We want to pass it through the network and figure out what parts of the network are actually producing this final classification result. For example, we want to look for things like legs or white fur that are being combined in different ways to produce the final result of a white wolf. So let's take a look at how we actually go about making these attribution graphs. Unfortunately, most modern neural networks are much larger than this illustration I have on the screen. So this problem boils down to some sort of selection in terms of the nodes and edges of the graph. Let's take just one picture of our white wolf and construct the attribution graph. We're going to take out the activations at a hidden layer of our neural network. So because we're using a convolutional neural network, the activations are in this 3D cube. So for one layer, we're going to have all these different 2D slices that correspond to one neuron each. We want to understand which of the neurons are actually the strongest firing or most activated for this particular image. So we're going to just take a simple max over this 2D slice, this matrix of values, and it's going to give us one number. And if we take the numbers for all these different neurons and then we sort them into this ranking, we get a distribution that's quite power law looking. There's only a few neurons that are really contributing towards this, this image. So the operation here is we're going to record these top neurons, we're going to forget about the others, and then we're going to do this for every single layer of our neural network. These neurons that are the top firing are now going to become the nodes in our attribution graph. Okay, so we're halfway there. We have the nodes, we just need the edges. So how are we going to do that? Well, let's take out the activations at, say, one layer earlier in our neural network. And we want to understand how each of these blue neurons influence just one green neuron in a following layer. So the way you would compute this green slice normally is you would distribute these red filters that are learned during the training process, perform your convolution operation, sum it all up, and you get your green slice. But we're actually going to break that operation in the middle. We're going to take a max of the intermediate output of that convolution operation. This is going to give us one value for every neuron. And now you can probably see the overall idea here is when you sort these values, it's once again quite steep on one side. So we're just going to record those top neurons that are most influencing just one particular neuron in a following layer. Forget about the others, and these now become the edges of our attribution graph. So from here, if we record this and we aggregate all these different activations and influences over every single image in a particular class, that is how we get the final attribution graph at the end. And what's really great is because we're using a graph-based representation for our technique for interpretability here, we can leverage decades of graph algorithm research, such as personalized PageRank, if we want to summarize the graph even further. We'll see a little demo of that here soon. Okay, so there's one last missing piece of the puzzle before we look at a demo of Summit and some of the really cool visualizations that it can make. And that is, how do we know what each individual neuron is actually detecting? So here we're going to use a technique called feature visualization. What feature visualization does is generate examples starting from random noise that optimize the image itself to activate just one particular neuron. So here I have a little animation of this one neuron in a large-scale convolutional model, and it looks like this fake image that it's producing is some sort of animal or dog nose with some sort of hair going out perpendicular to the snout. It's a little bit hard to see, so what we can actually do is give further evidence by showing dataset examples that also maximally activate this particular neuron in the network. And here we now have this synthetic feature visualization alongside different dataset examples that are highly activating it. And indeed, it looks like with pretty strong evidence there's this neuron has learned some sort of detector for a black circle, perhaps a nose with stripes or fur going out from the sides of it. Okay, so we have everything we need now, and I want to show you a little demo of our tool Summit working on the Inception V1 network. This is a large-scale prevalent convolutional model trained on ImageNet. So this is about 1.3 million images across 1,000 different classes. So our interface is right here, and as you can see, the attribution graph is the primary space in the UI. So if we zoom in here, we'll actually see that same neuron that we were just looking at with the dog nose. We're looking at the white wolf attribution graph once again, but we see these other features like pointy ears, the left and right side of fur detectors. It's pretty interesting that this network has learned something about orientation without ever being explicitly taught that. We also see more complex features such as white wolf faces, and then even white fur that's being learned towards the later ends of the network, which is confirming a suspicion that many people have about these types of networks. Remember when I said that these graphs are completely interactive, and because we're using a graph-based approach, we can actually use personalized PageRank to filter down the graph to just the most important neurons and their connections. But remember, white wolf is just one class of 1,000 classes. So we can actually zoom in and do a little bit of class similarity in this dimensionality reduction view in the top left. We can look at the other similar classes to the white wolf that this model has learned. And we see things like the Arctic fox, the timber wolf, and the red wolf, which is a pretty good sign that this network has learned something similar about wolves in general. Well, let's go to something else. Let's not look at the wolf anymore. I want to look at a completely different animal or class. For example, what if we looked at the tench, this sort of brown, green, yellow fish, and want to see what its attribution graph looks like? So in our system, you can just search for any one of the other 1,000 classes. So we'll find tench, we'll load it up. I just want to focus in on its attribution graph for a minute here. If we go towards the beginning of the network, we'll see things like edge detectors and circle detectors, pretty common use, these basic building blocks of vision models. You see these everywhere. But we also see these neurons that look like people forehead detectors and these chubby cheek and nose and other types of finger detectors that are happening early on in the network as well. And there's a whole bunch of different neurons that are looking at different parts of people. Well, that's pretty weird because remember, we're looking at the attribution graph of this tench fish. And it really isn't until the middle part of this network you start to see neurons with different types of scales, or other fish-like features that you would expect. But this last neuron that I want to highlight, it looks like there's some sort of bug on the palm of someone's hand, and that prompted us to actually go and look at the data set for what this class actually is. And when you do that, you actually see the trend is pretty immediately clear, that in almost every picture of a tench, there's someone behind it holding it as if they've just caught it from going fishing. And now this trend is actually on the entire data set. So there's about 1,300 different images of tench in this data set. And so this network has actually learned that if there is a person behind the fish, it's more than likely not a tench. And that may or may not be something that you want your model to know depending on your use case. But without Summit, you would have no idea that data bias and now the model bias is actually there. And you can extend this example even further. If you go and Google image search tench, you'll see that most of the people are also holding it just like this. So it just shows again that when you're building your data sets, there can be inherent bias that you just don't know about that our interpretability methods can detect. Well, let's make sure that not all fish have people in them as well. So I want to look at a different class, say one that doesn't have people holding the fish. Now a good bet would be the lionfish because their little fins are actually poisonous, so you definitely don't want to hold them. So we're going to take a look at what its attribution graph looks like, and indeed, there's no people features, which is a great sign, but there's still few fish features. There's not scales and things like you would expect. It's really borrowing textures such as quills and even a neuron that fires strongly in zebras for stripes that are highly activated and combining to form these high-level features that are used to understand lionfish. And now the last example I want to go over is perhaps my favorite, which is instead of just looking at a single attribution graph, we can actually compare them against one another. So here's an image where we've taken the intersection of the brown bear and the black bear attribution graphs. And what's really cool is now we can see if our model has learned something about the overall bareness within our data set. So these light gray paths are neurons and features and pathways that are shared by both classes, but then you can see the branching out the brown and black pieces that are specific to these two classes. So you can see that there's these brown fur and black fur detectors that our model is presumably using color here to actually distinguish these two classes from one another, which is what we'd expect based on just our understanding of what a brown bear and black bear should look like. So one thing that's really exciting is that this tool is completely open source, but not only that, there's a live demo that you can go play with. So at this URL up here, you can just load up the tool and you can play around with all 1,000 different attribution graphs loaded directly in your browser. You don't have to install anything. If you go to that URL, you're also going to see a button in the top that says, "What is Summit?" And if you click that, it's going to scroll you down a little bit to reveal this article that we've written directly underneath our live demo that contains examples, other visualizations, video demo walkthroughs, a little bit about what this research is, and links to the code, paper, data, so on and so forth. So we've really brought everything in here to sort of boost our research dissemination with this project. But Summit actually joins a handful of other projects, particularly within machine learning, that is using the web and interactive visualization to explain and get people onboarded with different types of research. And that leads us to this final part of my thesis that I want to talk about, which is how do we communicate interpretability? How can we boost research dissemination, boost machine learning literacy in citizens? Because as we've seen, machine learning really is everywhere. So we want to equip people with some understanding of how data-driven decision-making works. And so that type of research dissemination artifact I just showed you for Summit is something that people are calling an interactive article. Now, interactive articles are most commonly seen in the media for politics discussion and pop culture, popular on places like the New York Times and 538, where they're using rich graphics, visualizations, interwoven with text to communicate some sort of complex idea. So we thought, why can't we do this for interpretability? So that's exactly what we did. We authored this article. It's called The Myth of the Impartial Machine, that walks people through how a particular type of error, such as data bias, can then be learned into models, become model bias, and then lead to people making biased decision-making in this sort of negative feedback cycle. And we onboard people to common interpretability techniques too. But this article is really cool because as you scroll down, we use all sorts of things like interactive graphics to teach statistical properties, data visualizations as you'd expect. We're able to run simulations directly in the browser, so you don't have to install anything to see how these feedback loops actually work. We can also use animation to engage people in a particular paragraph or point, and then actually load machine learning models directly into the article as well. So people can play around with these parameters and see how different combinations of the parameters result in the final predictions. Now, we published this article with a collection of other articles on a new platform that I co-launched with one of my colleagues, Matthew Conlin, that we call the Parametric Press. And the Parametric Press was published just over a year ago now and saw sort of viral success. So we had over 250,000 people come view our little magazine over just its first year. It was on multiple front page of Hacker News appearances. We had Stack Overflow write on their official blog about us, as well as Fast Company Review. So it was a really great thing to see that people engaging with this new type of interactive article artifact to communicate complex ideas. And some of the favorite things that I saw is that within this article about interpretability, the myth of the impartial machine, it really helped teach people about machine learning's impact on their daily lives. My favorite two comments, just some poll quotes from Twitter here, is that it's one of the most accessible treatments of bias in machine learning that these people have seen. Now, more broadly, it actually gives us a slight glimpse of what an interactive reading future or communication medium could look like. For example, Jeff Atwood, who co-started or co-founded Stack Exchange, said, this is how textbooks should have worked since I was a kid. And so with this viral success that we saw, we really thought we could be onto something here. What if we try to build out this space a little bit more to help people with different topics within machine learning and then perhaps generalize, outside of it. So this first mini contribution I want to highlight in this final piece of my thesis is that we've been able to show that these articles can help broad audiences learn about machine learning and particularly its impact on their lives. But because this is a new medium, we don't really understand too well how people go about reading and interacting with this type of content. So we authored another article called The Beginner's Guide to Dimensionality Reduction that teaches people a particular technique, namely dimensionality reduction, that's commonly used in interpretability and data science as a whole. But the important part about this article is that we were able to record reader interactions at a very low level. So anytime someone is scrolling or interacting with, say, a slider or a button, we can record that and reconstruct their reading process. So here is just a quick video on the left-hand side of what this article looks like. You can, of course, go view this online as well, but it has all these images that are reacting and arranging themselves based on the parameters of how people are reading. We published this at VisXAI in 2018, and it won a Best Paper Honorable Mention Award. And so just as a one-slide highlight of all the different things that we found, we're really able to reveal different reader patterns. For example, we can find people who actually scroll very quickly to the middle of the article and then stop and something catches their eye and they engage with that particular graphic in a little bit more time. We also see people who do some sort of sanity check where they start at the beginning, they scroll to the bottom, realize that this may be worth their time, and now scroll back up and begin to dive in a bit more deeply. But besides just these two reader patterns, we can actually do a dimensionality reduction of people reading our dimensionality reduction article for some more macro analysis if we want to look at different types of reader structure. And then really excitingly to me is that we're able to do these content-specific design evaluations as well. So we're able to do these evaluations where you don't have enough people or data to run sort of a user study in the lab, but you can test things like sliders, specific button placements, how big a graphic should be, and see how much people actually interact in a real world setting. So the contribution here is that we're able to engage people with learning material, leveraging active reading and really engaging people with this research dissemination process and understanding machine learning more deeply. And so for the last piece that I want to highlight is what I sort of hinted at earlier, which is where we want to generalize a little bit and actually go outside of interpretability and machine learning and actually just look at this medium a bit more in depth to understand, why it's important and why we should care about it. So with my colleague Matthew and his advisor at the University of Washington, we authored this piece that is really about the theory and practice of interactive articles. And for one of the first times, connecting these two disparate areas and highlighting why people should care about this medium. And we show things like they lead to better learning and engagement. They can be used to spotlight important topics, and they also attract broad readership and acclaim. But the most exciting part is that instead of just putting all this discussion around interactive reading into a static PDF, we authored it as an interactive article itself, and we published it on Distill, which is the primary, or may I say maybe only, top journal that supports interactive articles natively. So let me just give you an example of what this work actually looked like. So in the article, we go through a number of different areas of why this medium can actually help people learn about different topics. And one of the affordances that this medium can provide is prompting self-reflection within readers. Well, we have this section, prompting self-reflection within the piece. We have some text and citations, making various claims, pretty standard, academic writing here. But as you go down, you're presented with this graphic of an incomplete line chart, and it prompts you to actually complete the trend. So it starts you off and it gives you this sort of trend, and it's really asking, what do you think has happened in the past? So if you go here, you can click and drag to complete the trend of what you think this particular data has done. And then when you're done, it'll actually highlight the ground truth data right behind your guess, and you can see how right or wrong you are. So this is challenging a reader's priors to understand what biases they may have in them against some data that's in the world. And this is really exciting because this technique has actually been run in lab user studies and has been shown to actually improve information retention within a reader. But not only do we have these interactive graphics to explain our topic, as you scroll down and we're describing specific examples, we actually pull in these small video snippets directly in line with the text so that people can read about these specific techniques and interactive articles and then just view some of the most exemplary sort of works that are highlighting that technique just right alongside it. But prompting self-reflection is just one of 5 affordances that we detail in this work. So the others, we go in depth about connecting people and data, making systems playful. This medium can help personalize reading and then also reduce a cognitive load within a reader's mind. And it's really exciting because in all 5 of these affordances, we provide interactive graphics and inline videos for each of them, just as I'd shown before. And we pull from 60 plus interactive article examples that have been published in the wild and marry that with over 100 other supporting citations, pulling from fields like visualization, education, psychology, and multimedia learning. And the last thing that this work does is outline some challenges for creating interactives, because there's not very many of them that are out there, despite sort of the survey that we did. So the first set of challenges is all around the technical aspects of authoring these things. So when you're writing a traditional research publication, you're authoring a PDF that people can read everywhere. But here we now need to design for diverse devices and make sure that it can be accessible and readable in the future, even when web standards may change. I think Amit Patel, who's Red Blob Games on Twitter, he's a really prominent interactive article author. He says it best when he says that plain text and PDFs will outlive websites, including his articles, and animated GIFs will still be around here. I think we all know just how accessible some types of content can be, so we want to make sure interactive articles are around for the long haul. After that, there's challenges for just authoring these in general. So it takes a pretty unique combination of editorial, design, and programming chops, and there's not a lot of tools that actually support that combination either. For example, in that Distill article I just showed you, if you wanted to just suggest a typo change, or maybe you saw something you want to comment on, what you have to do is go to our GitHub page and clone this repo, which already requires you to know a little bit something about Git, be comfortable editing and installing packages on the command line, then have some expertise in editing HTML, CSS, maybe a little JavaScript, and then you have to put all of that and open up a pull request just to make that typo. That's all incidental to actually this process of wanting to suggest something about the text, and that's way too much technical overhead, which is why it sort of is a barrier to entry for people trying to create this type of content. And the last challenge is actually around legitimization. So in non-journalism settings, oftentimes in research settings, there's a misaligned incentive structure for authoring this type of communication artifact. It just simply takes more time and effort than a traditional publication. And why would a researcher who's judged a pace, based upon how many papers and how many citations they have, spend that extra month or two putting together, a web-based explanation of what their research is doing if that's not the metric they're going to be judged on? So it's really great to see places like Distill that have so many eyeballs on them really push this medium forward. And even though we just published this article a few weeks ago, the response has been great. A lot of people really liking the techniques we're highlighting and implementing. And once again, Ben Steinemann was very nice to comment about this compelling vision of the future of writing here. And so the last mini contribution is, through this work, we were able to generalize out of interpretability to really synthesize unique affordances and formalize the future research challenges of this medium. So now we're getting pretty close to the end here. I just want to wrap up with some future directions of research that this thesis opens up. Take a sip of water real quick. So to summarize everything, if you were to put everything I just described and try to pack it into one sentence, you get my thesis statement here. But the punchline really is that all this work is helping researchers and practitioners enable interpretability within systems for model explanation, scale interpretability to deep neural network feature representations, and communicate interpretability to inform people about machine learning's capabilities and limitations on their lives. So some research contributions for the whole thesis in general. It really provides the first formulation of machine learning interpretability system design. This is primarily through our operationalization that provides a model for future investigations on how people are using interpretability tools in practice. But also we include these new scalable techniques for global model understanding. So this is primarily through Summit, but then also Gamut as well, where we've been able to show this first scalable graph representation for understanding neural networks trained on big data that combine both global and local explanations. We also have some other contributions as well, such as this new paradigm for amplifying research dissemination through our viral success engaging people in state-of-the-art work, through our work on interactive articles. This Distill work is also really a first of its kind to show interactive articles in the medium that it's describing. And much of these systems are open source to really help broaden people's access to state-of-the-art research and interpretability. So some impact that these systems have had, I've already mentioned Gamut and Telegam have been deployed and demoed at Microsoft Research and integrated into popular toolkits. Our work on scaling interpretability through Summit and our survey has been recognized by a NASA PhD fellowship. This has been supporting me for the past few years. But we've also claimed the top search result in Google for deep learning visualization, which is really exciting. So if you Google anything related to that, you'll find our survey is the top result. And then when it comes to communicating interpretability, our work on the parametric press and interactive articles has helped over 250,000 people learn about machine learning and provides the first formalization of interactive articles. So now to wrap up, I just want to present a couple of quick areas of future research that this thesis really opens up some rich spaces to explore. Along these axes of research, practice, and communication, that sort of sums up the whole story of my work. And this first one is all about mixed initiative model development. So we had this graphic from earlier where we show that we take data and from it train these machine learning models. But I think we all know this may likely not be the case. And this process is actually very iterative, and modeling can inform the data collection that you do. And so I have some other work that's presented at Chi just recently earlier this year, and then Viz last year, that tries to bring visualization and people into this model development loop to leverage the best of both worlds in terms of people and machine intelligence. And this opens up a number of interesting research directions around interpretability, which is, can we just rethink data collection from the beginning into a process that I like to call designing data, where we can actually bring in data diversity from the collection process and not consider it as sort of some afterthought of your workflow. And then from there, can we enable flexible analysis with some interested subgroups to do a little bit more rich understanding of what your model has learned besides just these local or big global explanations. And then lastly, one limitation of my thesis work is that all these interpretability techniques are focused just on one model, where we can control the inputs and outputs very well. But in practice, machine learning models are actually just one link in a chain of models where a developer may not have control over what's coming in and what's coming out. So we need some way to do multi-model interpretability to help us understand these larger machine learning systems. I'm also really interested to make interpretability a common practice. And here I want to leverage some of my existing work on enhancing programming tools, specifically Python tools like Jupyter Notebook, by just integrating and bringing these techniques directly into the programming environments that people are doing this type of work, and then observing them to generalize and create best practices for interpretability. And then here I have this little report card that I filled out for myself for research dissemination efforts. I've really tried to go above and beyond besides just publishing a paper and calling it dead, but actually having videos and open source code, live demos, and all these different things. And I think that really helps amplify research dissemination. So this last piece of future work is what I'm calling research distillation. And here, this is really bringing in interactive articles and other communication mediums to help onboard people and digest the state-of-the-art research. And I think that there could be better tools to help lower the cost of creation of these articles that could then also transform machine learning education at a larger scale. And so with that, I am very closely nearing the end. If you all are wondering where all these great ideas for future work are going to be done, well, some of you may already know, but others may not, that really excited to be moving from Atlanta all the way to Seattle to join Apple as a research scientist, where I'm going to be joining a brand new team focused on data visualization and interfaces for machine learning. So all those ideas I just mentioned, really excited to hit the ground running at the beginning of next year. And then if you've seen in any Apple keynote, you likely know their famous, one more thing slide. So before I wrap up, I have just a couple of last things I want to mention. And because this is a defense, I have a whole bunch of people to thank for this work. So before we get into a lot of the thank yous, I've actually been keeping a daily journal ever since I started the PhD. So you read that date correct, that's July 2015 all the way to today. And it's been really great the past couple weeks reflecting on my whole experience, scrolling through some of the pictures. I've written over 320,000 words, which is an interesting stat I pulled up. Really excited to dig into some of that data as well in the off time. But it's been great presenting my work at various places, getting to know the Georgia Tech Visualization Lab and Polo's group. Met so many different friends and colleagues, and have literally been to the center of the universe at NASA JPL. This is me and some other friends scrubbed up in one of the rooms where they're building some piece of the Mars rover. And so this long list of thank yous, bear with me, because there's a lot of people that's helped me throughout the past 5 years. First and foremost, Polo, of course. Polo has been nothing short of really an exemplary advisor, truly a fantastic mentor this whole time. He stayed up with me super late, editing pages and pages of writing for deadlines, is always responsive, and is fighting for his students every day. And I'm never going to forget some of my favorite Poloisms as well, such as make the font bigger, too much text, and move it up earlier. I think in 15 years, whenever I'm doing research, I'm still going to hear your voice in the back of my head saying these things. And for people who still don't know sort of the greatness that is Polo, if you just come to any one of the research meetings, you may be lucky to get a surprise sweetheart delivery too, which always brightens up everyone's day. There's also Alex and Chau at Georgia Tech who have been super helpful in guiding this thesis work over the past couple of years. I have to thank them as well, particularly Alex too, who I met in my first year, who showed me visualization as a research field very early on. Nathan really took a chance on me. He was my first mentor of my first internship over 4 years ago now, which is hard to believe. And he introduced me to the topic of interpretability as it was just sort of up and coming. I had no idea this would be my thesis topic, so it was really great to work with him and him over the past few years. Scott, Hillary, Maggie, and Santiago at NASA and JPL, they really taught me the importance of design thinking, rapid prototyping. And for anyone who saw my old desk at the space on Georgia Tech, it's these 4 people you have to blame for all the different sketching and, you know, maybe chipped paint on the walls that I hung all these, you know, different types of paper behind my desk. And then Steve and Rob at Microsoft Research, and Ham and Kayer at Apple. These 4 people really gave me the freedom to pursue my own ideas as I was hitting my thesis strides sort of later during the PhD, and gave me so much confidence in the work I'm doing. So I have them to thank so much for this work as well. But besides just mentors, I've met so many great friends and collaborators at places all around the country and world. People from the Polo Club of Data Science, Georgia Tech Visualization Lab, and of course have to thank NASA once again for this PhD fellowship that has been funding me the past 3 years. So in the very last slide, I would be remiss to not mention just a couple of other special people in my life here. So on the left is my wonderful fiance, Jessica, who has been here the entire time during this journey as well. We started dating just before this PhD. So our lives have been kind of intertwined with it ever since. So that's why it was really fitting that last year, just 2 days after I proposed my thesis, I convinced her that there was a conference in New York, and we flew up there sort of as a disguise when I then proposed to her. And it's been lovely having you by my side this entire time, helping me through all the difficult deadlines and writing and process like that. So I can't thank you enough. And then lastly, my parents, who are here on the right-hand side, really glad that they were able to join today and see me actually present this work that I've been describing to them over the phone for 4 or 5 years now. They really gave me the opportunity to find and follow my passion. So I just want to thank you both for helping me get to where I am today. And so with that, I think we can finally conclude. Thank you all for your attention. And Paul, I will let you sort of moderate the chat and questions here. If you all have questions, I'll be happy to take them now. Thanks so much.
Okay, thank you. So I think we can do a round of virtual clap. And thank you. And yeah, so right. So following our logistics. So now that after presentation, so we'll open up the virtual floor for the audience to ask any questions that they may have. So anyone is welcome to type your question in the chat, or you can just unmute yourself and can say anything. Well, I mean, questions, yes. So yeah, anyone, they're welcome. And of course, a lot of congratulations notes coming in the chat window as well. Any questions from the audience? You can unmute, or you can just type in the chat window. Yeah. So this is your last time to ask Fred a question before he is no longer a student. So yes. Okay. Any
It
questions
seems
from
like
the
every
audience?
conference talk I've given, I've had people lined up. So if for this final one, no one wants to ask up, I'm
Yes.
totally fine with that too. I feel like I've gotten my fair share over the past years.
Okay. Okay. Let's see. Okay, so we have a question from Andrew. Yes, a question. The GAM-Viz tool used for the housing prices is really cool. Can a tool like this be used to visualize or explain more complex feature interactions, such as feature X and feature Y being required before either adds value to a house?
Yeah. So one assumption of these generalized additive models is that they assume IID or just independent features. So if you want to actually squeeze some more performance out of them, the person who's really driving this model class at Microsoft Research, his name is Rich Caruana. He was one of the co-authors on that paper. He's building out these new types of models called GA2M, a little bit harder to say than GAM, but it includes those interaction terms that you were describing, these sort of like XI, XJ terms. Now the visualization there becomes a little more complex because you then have sort of a heat map of different values instead of just a line chart. But that's something we have looked at. There's no perfect solution for looking at uncertainty over those spaces as well. But the models exist, and in that interpret ML package, that's the actual class that they're using as well. So you can definitely use them, but the jury's out still on some better interactive tools to help explain them.
We have another question from Scott. So question about Summit. I can drop it here or save it for the committee discussions. So Scott is curious to hear Fred's thought on how Summit would work with non-image data sets.
Yeah, okay, so great question, Scott. Right now, so I should say the idea of aggregating activations and influences to make these attribution graphs, that idea is general and will work, as far as I know, with almost every neural network model that's out there. The only problem is with non-image data, getting those synthetic images, those feature visualizations, is not quite clear what those would actually look like for non-image data. So you could certainly build attribution graphs for NLP models, also multi-layer perceptrons, or just non-image, neural networks. You could build those up. Everything would be great. You could do some analysis like similarity, see how they compare, the distributions of each of these top activations, but you just don't have that rich feature visualization to help you say, this neuron is detecting X or Y. So the technique works. I think it would be extremely helpful and exciting to see it on non-image data, but you just are missing that last little link, at the end of the day for the feature visualization.
Okay, great. Any other question? Oh, there is a question from Ian. For the interactive articles, are there any meta frameworks that would help writers make articles from chunks in quote? For example, dragging and dropping different viz types into the article. Maybe you mentioned this and I missed it.
So that is actually a really cool research idea. So there's a couple of tools I can point you to. One of them is the PhD work of my collaborator, Matthew Conlin at UW. He's building out a toolkit called Idle that helps people author interactive articles with some nice built-in components. It's all based on React. So you can, if you're familiar with JavaScript, you can author interactive articles much easier using his toolkit. So I'll definitely point you there. But in terms of just removing more of that sort of technical overhead, there's other tools that do visualization recommendation just based on whatever data you have or what insight you may be going for. I know Steve Drucker here, and I'm not sure if Arjun and others are here as well. They've been working a lot in this space over the past few years. So it would be really cool to marry those two approaches to say, come with your data set. We'll recommend sort of some really interesting visualizations or data facts that we have found in it, and then let's also stitch it together in an article to either publish on a blog or share out to some of your friends. So it's kind of like a Jupyter notebook in a way, but you could maybe not have to program as much in there. So super cool idea. I think there's a lot of open space for better authoring tools of that type of work. So yeah, I think you're hitting on a pretty good open research problem there.
That's great. That's probably take another 1 or 2 PhD to do. Yes.
Yeah.
Any other questions from the audience? Yes. Question. Last chance. Last call. Okay. Okay. So Ian said, I prefer not to relearn JavaScript if possible. Yes, I think all of us wish doing. Yeah.
Relearn is the key
okay,
word
great.
there.
Yes.
We all do it.
Okay, great. So I think we have given everyone all the chances to ask first questions. So no more questions from the audience, and thank you everyone, families and friends, for joining us again today for Press Defense. So thank you all, and now it's time for us to kick you out. So for all the audience, we'll kick you out. Now you can drop from the call, and then we'll stay with the committee, and then the committee will continue to ask questions. So we'll take probably like one a minute for everyone to leave, and if you don't leave, I'll kick you out. So no worry. Okay, we'll
that sounds great. Thank you, everyone.
Yeah. Thank you for joining.